In this video lecture, we'll be solving this problem all nodes distance k in binary tree, which is a Leetcode medium problem. In this problem, we're given the root of a binary tree, the value of a target node in the tree, and an integer k. We have to return an array of values of all nodes that have a distance k from the target node, and we can return the answer in any order. Fine. So we are given a binary tree, a target node, and an integer k. We have to return the set of values of those nodes which are at k distance from the target node. Fine. So in the input we will be given the root of the binary tree, the target node, as well as the distance value k, and in the output we have to return the array of the nodes which satisfies the given conditions. The number of nodes in the tree lies in the range from 1 to 500, while the node value goes from 0 to 500, and all the node values in the tree are unique. Target is the value of one of the nodes in the tree, and the distance goes from 0 to 1000. Fine. So let's better understand the problem statement using an example. So here we have an example. So in this binary tree, this is the target node, which is 5, and we want to find the nodes which are at a distance of k is equals to 2. Fine. So we can see that from this node 5, the nodes which are at a distance of 2 are 7, because we are 2 edges away from 7. Here 1, 2, 4. This is also a valid node, and this node, this one, it is also two unit away from the target. Hence, the set of values for this particular test case would be 7, 4, and 1, and that's the answer for this particular binary tree. So how do we solve this problem? Let's think about it. We can see that this is my target node, and I want to find all those nodes which are at a distance of k from this node, and this is a binary tree, and we know the structure of a binary tree, and we know the node structure of a binary tree. So this is the node structure of the given binary tree. We have 3 elements in there. So for each node we have data in that node. We have a pointer to the left subtree or the left child, and a pointer to the right child. So these 3 elements we have for each node, and here from each node we can either move to the left node or to the right node. We cannot move to the parent node. Fine. So this is true for all the nodes of this binary tree. Fine. So how would I find those nodes which are at a distance of k? The very first idea is to run BFS algorithm on this particular problem, starting from the target node, that is 5, and in the BFS we know the working of BFS. We explore all the adjacent nodes for a particular node, and we push them into a queue, and then we process those nodes in the order in which we pushed them. So the queue that we use follows first in, first out order. Fine. So let's see the working of BFS for this particular. So the very first idea which comes into mind to solve such type of problems where we have to locate nodes at a certain distance would be the simple graph traversal or tree traversal algorithms, which are DFS and BFS. Fine. So let's try to solve this problem using BFS. So I'll be using BFS algorithm to solve this problem. Let's see if it works. You can see that starting from the target node in BFS, I try to push all the adjacent nodes into the given queue that we use in BFS. Then I process the nodes which I pushed into the queue in the order in which we pushed them. Fine. So initially we have node 5 with a distance of 0. So we know how BFS algorithm works. We take a queue, we push the source node with its distance into the queue, then we run the while loop till this queue is not empty, and we pop the front element from the queue. So we pop 5, 0 first. Then from this node 5, I try to traverse all its adjacent nodes. So what are its adjacent nodes? We can see that since it is a binary tree, we can only travel to left and to the right. So I can check for the left child, and I can check for the right child, and the pair that I will be pushing into the queue for the left and right child would be and 1, while for the right child it would be 2 and 1. Why? Because 6 is the node number here, and it is at a distance of 1 unit or 1 edge from the source node. Hence I am putting 1 here, and this can be calculated simply by adding 1 into the integer which is present at the parent node. So we had 0 and we go one step to the left, and hence I add 1. Fine. Same goes for the right child. But the problem is, how would I go to the parent node? Because we can see that the parent node 3 is also at a distance of 1 from this target node. So this is our first problem which arises while running this BFS algorithm. So how would I solve this problem? So we can observe that one node has exactly one parent in a binary tree. We know this fact. Hence, I can map each node with its parent value. So 5 can be mapped with 3. Similarly, this 6 can be mapped with 5. This 2 can also be mapped with 5, because we know that all the values in this binary tree are unique. We know this fact from the problem statement. Here we know that all the values in the node are unique. Since all the node values are unique, we have a perfect mapping. So for each node we have a parent. So for 6 we have 5 here, then for 7 we have 2. So in this way I can map the values, I can map the parents for each node. How would I do that? How would I implement that? It is easy to implement this type of functionality. I can simply use a hash map. So use a hash map of type node. So I will use this type of hash map in which the node maps to node, or a node maps to its parent node. So for each node I can simply get my parent node from this hash map in a constant time complexity. Fine. Hence giving me the parent along with the child. So for this particular node where I started my BFS, I can traverse to the parent, which is this, and hence the pair for the parent would be 3, and I push these pairs into the queue. Okay, so that's how I push these pairs in. Okay, so this is my queue in which I have pushed 6, 2 and 3. Then I process the node 3 and I pull it out of the queue. So for 3, 1. So also I will keep a visited array which will be used to mark the visited nodes in the queue. So here I have visited 5, I have visited 6, I have visited 2, I have visited 3. Fine. So then I pull my 3, 1 pair from the queue and I go to the adjacent nodes which are not visited, and I see only one such node, which is this one. So the pair for this node would be 1 plus, because the distance for the parent node, which is 3, is 1. So it is at a distance of 1 from the target node, and hence this node 1 would be at a distance of 2 from the target here. Fine. So I will be pushing 1, 2 for this node. So I push 1, and here I have marked this 1 as visited. Then I will pop 2, 1 from this queue, and for 2, 1 I will go to the adjacent nodes which are not visited. So such nodes are 7 and 4. So we have 7 and we have 1, the pair for node 7, 7 and 2, and for the another node we have 4. Remember the problem statement, we wanted those nodes which are at a distance of 2. Have we find such nodes? And answer is yes. We have found 1 here, so I push 1 into my resultant array. Then I have found 7 here, so I push 7 into my resultant array. Then I have found 4 here, so I push 4 into my resultant array. And the order of these integers does not matter. Fine. So I have visited these nodes as well. 7 and 4 are visited. Then I push 7, 2 and 4, 2 pair into the queue. Then I pull 6, 1 from the queue. So we have pair 6, 1 here. Then I move to the adjacent nodes of 6 which are not visited yet, and I see no such node. We have 6 as it is here, while 5 is already visited initially. So this is simply out. Then I pop 1, 2 from this queue and I move to the adjacent nodes of 1 which are not visited, and these nodes are this 0 and 8. But we can see that these nodes 0 and 8 are at a distance of 3 from the target node. Fine, because 1 is at a distance of 2, and hence this 0 and 8 will be at a distance of 3. So there's no meaning in pushing these nodes or processing these nodes further. So I continue my BFS right from here. So 1, 2 is removed from the queue. Then I explore 7, node 7, here this one, and I try to visit its non-visited adjacent nodes, and I find no such node because 2 is already visited. So this is again out. Then I come to node 4 here, and same goes for 4. We do not find any non-visited adjacent node, so this is again out, and we end up with the empty queue. Fine, and we have our answer array prepared. It contains 3 nodes, 1, 7 and 4. These are the 3 nodes which are at a distance of 2 from this target, and hence this is our answer. So let's see the implementation of the same approach in the next slide. So first we want to annotate the tree. So we know that first we have to map the value for each node to its parent. That process is called annotation, and we will do this using depth first search. So we start our depth first search from this root node while passing the parent for each node, and for the root node the parent would be null, and we use a auxiliary map, hash map, to map each node to its parent. So that's what we are doing here. We first declare a hash map MP, which is used to annotate the given binary tree. Then I perform my depth first search where I pass the node and its parent. For root node, I pass the parent as null. Then if the node is a leaf node, then I return right from there. Otherwise, I map the node to its parent. Then I recursively call the same function for the left subtree and for the right subtree, so that they can be mapped as well. So this will perform my annotation. Let's see how BFS will work after we have performed this annotation. So here we have our distance k function, which takes in the root of the given binary tree, the target node and the distance variable. Then this is my base condition. If we have an empty tree, then I return an empty array. Otherwise, I first annotate my tree right here. So this will basically map each child to its parent so that I can move to all adjacent nodes of any node in the binary tree. Then I declare a queue of pair node with int, where the node represents the node of the binary tree and int represents the distance from the target node of that node. Then I push the target node, or the node from where we will be starting the BFS, with the distance as 0 because this is the source node. Then I declare a visited array, which is used to check for the visited nodes so that they are not visited again, and I mark my source node as visited, and I run my while loop till the queue is not empty. I pop the front element from the queue. I check if its distance becomes equals to k, which is the required distance. In that case, this node is one of our target nodes or required nodes, and hence I push this node into my resultant array. So this res is the resultant array, and I continue right from here to process another node in the queue. Otherwise, we have 3 conditions. The first one is check if there is a left child. If there is a left child and it is not visited, in that case I push the pair for the left child, which is the left child along with its distance from the target node, which will be incremented by 1 from the distance to its parent node, and I mark it as. Then I check if there is a right child. If there is and it is not yet visited, then I push the pair for the corresponding right node, that is the node itself and its distance from the target node, which is equal to the distance for its parent plus 1, and we know the distance for the parent, which I extracted here. So this represents a pair, and its second element represents the distance of the node, which I extracted here. Then the third condition is used for checking the parent, and here we come. So here we will be utilizing that annotation strategy which I implemented initially. I will be checking if there is a parent for the current child. If there is, then in that case I will check if it is visited or not, and if it is not visited, then that has to be included into the queue, because that can become one of the potential candidates for finding our k distance node, and hence I push this node along with its distance from the target node or from the source node from where we started, and I mark it as. Finally, I have my resultant array prepared after I empty my queue here, then I return my resultant array right from it. Fine. So this is how this BFS function is working. Let's see the code implementation for this particular ID. Okay, so this is my solution class. We have two functions here. The first one is depth first search function, which will be used to annotate the given binary tree, which takes in the root node and the parent. So for each root, I will map it to its parent, and this is my distance k function, which takes in the root of the binary tree, the target node, and the distance variable. It returns the set of values which contains the nodes which are at a distance of k from this target node, a node and its distance from the target. So here I globally declare the resultant array as well as my hash map, which will be used to annotate the given binary tree. Then here is how the annotate function works. If the root is null, then I simply return. Otherwise, I map the root to its parent. I recursively call the depth first search function for the left child and for the right child. So this is the empty tree, a case of empty tree. Then I call my depth first search function to annotate the binary tree. Then I push my target node along with its distance into the queue which I declared, and the queue is of this type distance. Then I declare my visited array, visited array, which will be used to mark the visited nodes in the given binary tree, and I mark my target node as. Then I run the while loop, and in the while loop I simply pop the front node from the queue. I check if its distance becomes k. If it is the case, then I push this node into the resultant array because this is one of the target nodes, and I continue right from here. Otherwise, we have three conditions. The first one is check if there is a left child and it is not visited. In that case, push the left child along with its source node and mark it as visited. Same goes for the right child, and same goes for the annotated parent. Finally, I will have my resultant array prepared and I will return it right from here. So this is how the function is working, and it is the implementation in C++. Let's see the implementation in other language. So this is the implementation in Java. So let's see the time and space complexity for this particular solution. You can see that we are performing BFS, and we know that the time complexity for the BFS is big of n. The space complexity for the given problem is big of, because I am performing BFS, and in BFS I'm using a auxiliary. The stack space consumed is big of h, because where h is the height of the binary tree. So this is the stack space which we consume here, and this is consumed while performing depth first search for the annotation. So that's all for this video. If you like the video, then hit the like button and make sure to subscribe to my YouTube channel and give your feedback in the comments below. I will see you in the next video. Till then, take care. Bye bye.